All right, so for this lesson, we're going to be doing a lot of stuff out of that is rather not in your module, and I'm actually going to put a couple tables up here that aren't in your module, because unfortunately you need to do rate of change, and in the homework there are some great rate of change problems, but they don't have any problems like that in the actual lesson. I'm not sure what happened, why there's a disconnect, but there is. Eureka wants you to go through this kind of this exploratory activity where you do a lot of discovering. And really, for our purposes, and for the sake of the amount of time that we have, we can get through this a lot quicker. So, let's do that. So the first thing we need to just talk about is all right, so first thing we need to do, we're going to work with Euler's number, E, later on. All you need to know is what it is, that it's a number. It's represented as a letter. It is an actual number. It's an irrational number, right? Because it's saying that E is approximately this value because it just keeps going on forever and ever and ever. It looks like it repeats, right? Because you see this. It looks as if it repeats because you see this 1828, 1828, but it doesn't. It continues on forever and ever and ever, like pi, right? It's another one of those numbers that continues on forever and ever and ever, like pi. You can actually calculate its actual value in your calculator. You have an E button on your calculator. It turns out to be sorry, it's hard to see, but if you hit second and then the ln, well, maybe it did not hit second. Second, there we go. And then ln, it gives you E. And if we want to know what E is, we would just say E to the first power, right? And that gives us what E is. And again, if you be careful, because it looks like, if you look at it in your calculator, just because of the digits that it rounds it to, it looks like that 1828 repeats, but it doesn't. It does change after that last 8. So we'll deal with Euler's number later on. Just wanted to show it to you, show you that it's an actual value. It helps you deal with logarithms, natural logarithms, which is going to happen in the next topic. In topic B, we'll be looking at logarithms. So it's just like a little preview, a little foreshadowing. And then we're going to go right into rate of change, right? So, unfortunately, this is not in your module. But you do have homework in your module that looks a lot like this. So, here you go. Rate of change is very closely related to slope, right? You remember, you could count your slope, and that was like your rate of change. It's very similar. We could look at the slope of these things, what they are. So population graphs. So we're looking at U.S. population, world population. Callie says it looks like the U.S. population grew the same amount as the world population. She says that can't be right. And we're looking from the years 1950 to 2000. And Joe says, well, I don't think they grew by the same rate, but they sure grew at the same rate. Look at the slopes. Wait, hey. So let's look at them. So if we were to look at the slopes, right? We're talking about rate of change. remember, if we look at the slopes, remember it was our change in y. Some people say rise over our change in x, right? You would call that our rate of change, right? So over here, we have our change in y over our change in x. And it does look like those slopes are very similar. Okay, so those slopes they do look about the same, don't they? All right. So let's say, is Joe or Kelly correct, right? So let's calculate those slopes real quick. So we'll call this one, remember your slope is 1. So we'll call this n sub 1. How would we calculate our slope? You remember we would go, remember it was y2 minus y1 over x2 minus x1, all the way back from over there in algebra 1, yeah? So in this case, y2 is 6,000 minus y1, I don't know, 2,500. And let's call this year where are we at? This graph is before. I don't know what's going on. Anyhow, trying to figure out our x values. We could use 1950. It's really better to call this year 0, 1, 2, 3, 4, and 5. It's a nicer way to represent this. And if we do it in that way, it's fine. So let's say we go from 5 to 0. Or how many years is that really? This would be 10, sorry, 20, 30, 40, 50. Sorry, my bad, right? That's better. So we go 50 minus 0. So we calculate that. 6,000. So our rate of change here is 70. What does that mean? That means that for each 10-year increase, there was an increase in population by 70 million, right? The population increased 70 million every 10 years. That's what that number tells us. Okay? So we could go million per 10 years, right? How about our second slope over here? Well, it looks like, I don't know, this looks like 280 maybe? 275? Alright, fair enough. 275? I can't write. I wanted to go with the, I was excited about writing 7, I guess, so I wanted to write it first. 275 minus 150. All over. And our x values, our last x value, so again, it's 50, right? We'll say year 50 over year 0. So 275 minus 1. I am messing this up. Sum done. I could probably do this in my head, but I'm not going to. $2.5 All right. So we're saying that, and this is in millions, right? World population, U.S. population in millions. So this is 2.5 million for 10 years, right? Is our rate of change? It's in 10 years, so I don't know why these hash marks are here. They're in the wrong spot. Looks like they belong there, right? I'm not sure whoever created these graphs. Well, Excel created these graphs. And Excel, I don't like. For awesome for business. Amazing for all of that stuff. But for, I don't know, scientific analysis, there are way better computer programs.
Yeah, could they have written in 5-year check marks instead of running something?
They could have, and you would have still had the same rate of change, right?
Would you have just written every 5 years?
Yes, every 5 years. And the number, and you would have wound up with 35. Sorry, every 5 years. So yeah, here this would wind up being 35, right? Every 5 years. And this one, you would just divide that by 2. Right, so 1.25 every 5 years. That's all. Because if you're going to decrease this by half, this is going to be decreased by half. Because the ratio is still the same. Alright. So, did we answer who's correct, Joe or Callie? Joe said the U.S. population grew the same amount as the world population. No. That can't be right, and it's not. And then she said they grew at the same rate, and that's not true either. So, but hey, we know the rate of change, and that's good. Okay. So again, world population, we have this table. Let's do the increase. All right, so now let's talk about the formula that you guys have in your book for rate of change. It's over there on 43. So it's f of b minus f of a over b minus a. This is your rate of change. Okay, so essentially, well, let's go ahead. I'll label these things. I'll label them on here. 1950 to 2000, okay? Where are we at? 1950. And I am so sorry that there's nothing like this in your book. I'm going to call this A, and that's B, okay? They're like X and Y, right? So if you were to put it into like your slope terms, right? This would be X2, and that would be X1, right? If you were to put it, it is the same as your slope formula, just with different notation. Okay, this here, these are your Y's, right? So, but this is f of A, and this one's f of B. Same thing as y1 and y2, okay? So we use our rate of change formula, and we do, right, so that's f of B minus f of A over B minus A. So f of B is 6,070. F of A is 2,519. B is yeah, we could do that. We could do 2000 minus 1950. It works either way. I feel like it's kind of nice to write it in terms of actual years that passed, right? But it's going to come out anyway, so get 50 either way. So 6,070 minus 50. So we get an average rate of change of 70.02. 70.02 what? Million people? Yep, and that's going to be for 15 years. Not too bad, right? It's really not bad. Alright. How does the percent increase for the world population compare to that for we just have the world population, so don't worry about that. That's your homework. And